Hello everybody, we're getting ready to do lesson 11.3 part 1 today of pre-calculus math. It'll be the classwork lesson. And for today's classwork lesson, part 1, 11.3, the tangent line problem. And for your notebook, it will be 18 points, so go into your notebook or your notebook guide, have those ready. And then 42 points into your classwork guide. For today's lesson, students, put your name, date, period in my classroom. Homeschoolers and onliners, put your due date there. And today's bell work, teachers, students, here's today's bell work. Sketch the graph of these rational functions here, students. So sketch the graph over here on these grids. Do any work that you need to do over here. And I'll give you 6 minutes. Pause the video for 6. Welcome back everybody for today's lessons. So we're going to sketch the graph of f of x equals 1 over x squared minus x minus 2. So the way that graph would become sketchable is we're going to factor the denominator, x plus 1, x minus 2. We have intercepts here of 0 and negative 1/2. Then you have a vertical asymptote here of x equals negative 1, x equals 2 from here from your factoring. And then your horizontal asymptote will be y equals 0. And then the sketch of that would be like that. This is what this graph should look like, students. And then down here, x minus 2 over x squared minus 4x plus 3. Factor it back to x minus 2 over x minus 3, x minus 1. And then we have intercepts here at 2, 0. And then 0, and then negative 2 over 3 would be more intercepts. Then we have a vertical asymptote here of 1 and 3 gotten from this here. And then y equals 0 again will be your horizontal asymptote. And this is what that graph will look like. Today's lesson. Tangent line to a graph. So calculus is a branch of mathematics that studies rates of change of functions. If you go on to take a course in calculus, you will learn that rates of change have many applications in real life. Earlier in the text, you learned how the slope of a line indicates the rate at which a line rises or falls. For a line, this rate or slope is the same at every point on the line. For graphs other than lines, the rate at which the graph rises or falls changes from point to point. The parabola in this situation here is rising more quickly at the point x1, y1 here. It's the slope here is steeper. Then at the point of x2, y2, which is up here, it starts to flatten off as you go up here, and then does the same thing down on the other side. At the vertex x3, y3 up here, the graph levels off, and at the point x4, y4, the graph is falling. So, it changes with a parabola. The slope is changing. To determine the rate at which a graph rises or falls at a single point, you can find the slope of the tangent line at that point. In simple terms, the tangent line to the graph of a function f at a point, say x1, y1, is a line that best approximates the slope of the graph at the point. So like this, here's your point here. A tangent line will determine the actual slope of this curve at that point here will be the tangent line. And then at this curve here, this point here, the slope of that point can be determined by finding the slope of the tangent line at that point. And then down here as well, the slope at this point can be determined by the tangent line. From geometry, you know that a line is tangent to a circle when the line intersects a circle at only one point. So here's another tangent line here. Tangent lines to non-circular graphs, for instance, in the first graph, like this one, if the tangent line were extended, then it would intersect. It would intersect the graph at a point other than the point of tangency. So it would probably intersect way down here, and then maybe if this thing curves up, which I doubt, well, it might, it would intersect it up there. So it would intersect at more than one point. Slope of a graph. Because a tangent line approximates the slope of a graph at a point, the problem of finding the slope of a graph at a point is the same as finding the slope of a tangent line at that point. So that is your problem, is tangent line slope. So we're going to try that here. Visually approximating the slope of a graph. Use the graph to approximate the slope of the graph of f of x equals x squared at the point 1, 1. So at this point here, we can draw out this line and then draw up that line after we draw this tangent line here. And good old rise over run should tell us what we have. From the graph of f of x equals x squared, which is this, you can see that the tangent line at 1, 1, which is right here, rises approximately 2 units for each unit change in x. So for each run unit, it has 2 units of rise. So you can estimate the slope of the tangent line at 1, 1. Change in y over change of x would be 2 over 1. So we have 2 over 1, which equals 2. So that would be the usage there of a tangent line to find the slope of this curve at this point there. Because the tangent line at the point 1, 1 has a slope of about 2, you can conclude that the graph of f has a slope of about 2 at the point 1, 1. We can pretty much assume that pretty easily. Well, let's try one here. I used a figure, here's our figure here, to approximate the slope of the curve at the point xy. So we have this point here, and then down here, students, this is yours. So I saved the good one for you. But for this one here, it is easy to say that this tangent line here has a slope of 0 at xy. That's pretty easy to say that. When you are visually approximating the slope of a graph, remember that the scales on the horizontal and vertical axes may differ. When this happens, as it frequently does in applications, the slope of the tangent line is distorted, and you must be careful to account for the difference in the scales. So take that into consideration as well. And I think we try one now. Approximating the slope of a graph. Example 2. Graphically, this graph graphically depicts the monthly normal temperatures in degrees Fahrenheit for Dallas, Texas. So approximate the slope of this graph at the indicated point. So we have a point here at 1069. And give a physical interpretation of the result. So here's our months down here. And then we have a jog here. So we make a leap here, and we start our graph at 30 and we go up to 90 here. So that's a lot more convenient than just listing temperatures that aren't going to be really relevant. So we make a jog and we start 30, 40, 50, 60, 70, 80, 90 in temperatures in Fahrenheit, and then here's our months. And then 1069 would be October, and then the temperature would be 69 degrees. So From the graph, you can see that the tangent line at the given point falls approximately 16 units for each 2-unit change in x. At this point here, we drew like a square, a corner here. And when we got that, we got rise over run would be negative 16 over 2 is what we got here. So you can estimate the slope at the given point to be what? With a rise over run, a 16 over 2, a negative 16 over 2. To be, slope equals change of y over change of x. So we have negative 16 over 2. And that gives us a negative 8 degrees per month slope of temperature change. This means that you can expect the monthly normal temperature in November to be about 8 degrees lower than the normal temperature in October from this graph here, from finding the slope of the tangent line. So let's try another one here. Use the figure to approximate the slope of the curve at the point xy. Here's our point xy. Students, this is yours down here. So for this one up here, what we have slope is 1/2, because at xy, y is a 1/2. Well, we have a rise here of about 1 degree with a run here of 2. So it's about, looks like it'd be about right. Rise over run would be 1 over 2. So you can estimate it that way. Slope in the limit process. So in examples 1 and 2, you approximate the slope of a graph at a point by creating a graph and then eyeballing the tangent line at the point of tangency. A more systematic method of approximating tangent lines makes use of a secant line through the point of tangency, and the second point on the graph is shown. So now we have this point up here, we have this point down here. We call this line, which goes through the curve, it's called a secant line. This is your secant line. This is h, and then this is f of x plus h minus f of x. So that is the length of this line here. So now we got a secant line. If f of x is the point, which is right here, of tangency, so we have a tangent. We want to find what the slope is of this line here, of this tangent line to that point. And x plus h, f of x plus h, which is this point up here, is a second point on the graph of f. Then the slope of the secant line through the 2 points is given by the slope of a secant line, f of x plus h minus f of x over h. So we have rise over run. Here's our rise, and then here's our run. So there is your slope formula for the slope of a secant line. The right side of this equation is called the difference quotient. This is your difference quotient there. The denominator h is a change in x, and the numerator is a change in y. The beauty of this procedure is that you obtain more and more accurate approximations of the slope of the tangent line by choosing points closer and closer to the point of tangency as shown. So as this point moves down to here, you will get a tangent line. It'll change the slope of your secant line, but you'll eventually get a slope of your tangent line. So we're moving down the curve here. This is your f of x plus h minus f of x changes here, x plus h, f of x plus h. And we get closer and closer to x, f of x. So we move We're moving down the curve, and we're getting closer and closer until we get a tangent line here at x, f of x. So this other point keeps moving down the curve, and then that's how we eventually get a tangent line. Definition of the slope of a graph. The slope m of the graph f at the point x, f of x is equal to the slope of its tangent line at x, f of x, and is given by m equals the limit as h approaches 0 for the the slope of a secant line, which now we put into a difference quotient. There's our difference quotient for that, provided this limit exists. Okay. So let's try one now. Finding the slope of a graph. Again, find the slope of the graph f of x equals x squared at the point -2, 4. So find an expression that represents the slope of a secant line at -2, 4. So here we set up our difference quotient. We plug in our values here. We know x is -2. So f of -2 plus h minus f of -2. We plug in our x into our difference quotient, and then we substitute f of x into x squared, which we did here. -2 plus h, that is our x squared. That's squared here. And then this is -2. That would be x squared as well. So we have our two x squareds here over h. So now we simplify this by expanding out. We got 4 minus 4h plus h squared. That is this, and then minus 4 here. Minus -2 squared would be minus 4 over h. And then we have -4h plus h squared over h. Simplify further. Then we factor out an h. Then these can cancel from that. Then -4 plus h. So -4 plus h. That would be our simplification from that. H cannot equal 0. Next, take the limit of m secant as h approaches 0. So as h approaches 0, from our original calculation here, -4 plus h. So if we turn our h into a 0, we get a slope here of -4. So the graph has a slope of -4 at the point -2, 4, which is over here. And that that m equals -4 here at -2, 4. So that would be what our tangent line is there at -2, 4 by using a difference quotient to do that. So let's try one. Use the limit process to find the slope of the graph of the function at the specified point. We have a 3, -3. Use a graphing calculator to confirm your result. So we have x squared minus 4x. That's one we're going to do. This is yours down here, students. So up here, here we're going to plug in our values into our difference quotient here. 3 plus h up here for x. 3 plus h minus g of 3, which would be 3 again. And then we're going to expand it out because we have x squared minus 4x. So we have our x squared minus 4x. And then minus a -3. See, minus a -3 here. That's our g of 3 there over h. And then when we expand this out and then simplify it, we end up with h squared plus 2h over h. So when we do that, we have h plus 2 as h goes to 0. This will all become 2 when you combine like terms. Your h's will cancel. You have h plus 2 here, and then as h goes to 0, your slope will become 2, is what that will be. And that is your 11.3 part 1 classwork lesson, pre-calculus math, animated PowerPoint math video at AOL.com for course materials or questions. Thank you very much.